Now let us extend our discussion of the entropy rate balance equation to open systems. In an open system, mass can enter and exit our system. Thus, we can modify our entropy rate balance equation to take into account these mass flows. Our ERB becomes the time rate of change of entropy within our control volume is going to be equal to the time rate of heats that are either supplied or removed from our control volume at a boundary temperature, plus the sum of our mass flows into our system carrying a specific entropy, minus the sum of our mass flows exiting our system carrying a specific entropy, plus any entropy generation rates we have. We see the first term on the left-hand side is our time rate of change of entropy within our control volume. Our second term is the rate of entropy transfer associated with all heat transfer processes. Our third and fourth terms are the rate of entropy transfer into and out of our systems by our respective mass flow rates, and the fifth term is our entropy production due to irreversibilities within our control volume. Now, with our ERB, we have a complete set of equations that we can evaluate the performance of devices with. First, we have the continuity equation. The time rate of change of the mass within our control volume is the sum of the mass flows in, plus the sum of the mass flows out. Then we have our conservation of energy equation. The time rate of change of energy within our control volume is the rate at which heat is applied, less the rate at which work is done, plus the sum of the mass flows into our system, carrying an enthalpy, a kinetic and potential energy, less the sum of the mass flows out of our system, carrying an enthalpy, kinetic and potential energy. And lastly, we have the entropy rate balance equation. We note that Q dot typically comes from our conservation of energy equation and then populates our entropy rate balance equation. To see this in application, let's consider two steady-state systems that heat a stream of air from 290 to 320 Kelvin at a constant pressure of 100 kPa. That is, we have a heat exchanger where we have a flow of air that enters at 290 Kelvin and exits at 320 Kelvin, and it undergoes a constant pressure heating process. The first system uses viscous dissipation of a fluid surrounding the airline to provide the heat to the air. The second system uses condensing steam at a constant pressure of 100 kPa that goes from a saturated vapor to saturated liquid to supply heat to our air. We want to determine the rate of entropy generation for each system, neglecting heat transfer to our surroundings. To begin, we apply our entropy rate balance equation for our air stream. That is, we have a single stream where we enter at 290 Kelvin and exit at 320 Kelvin. Since this is steady state, there is no time rate of change of entropy within our system, and we do not have any heat transfer occurring between our heat exchanger and our surroundings. Thus, we'd have the mass flow rate of our air times the change of our entropy between our inlet and exit being equal to the negative of our entropy generation. Or, solving for entropy generation on a per mass basis, sigma dot per m dot would be S2 less S1. Now, using the expression for entropy change of an ideal gas based upon standard entropy, i.e. table A-7-1, since this is a constant pressure system, our change of entropy is merely going to be the change of our standard entropy evaluated between our two temperatures. That is, our rate of change of entropy per mass flow rate is just going to be the difference of our standard entropy, or 0.09892 kilojoule per kgK. Now, for system 2, we must apply the conservation of energy to our systems, ignoring our kinetic and potential energies in heat and works, to express the ratio of our mass flow rates. We have a heat exchanger where air enters at a temperature 290 Kelvin and exits at a temperature of 320 Kelvin. Steam is entering as a saturated vapor and exits at a saturated liquid. Thus, our conservation of energy equation becomes 0 is equal to m dot air, H1 less H2, plus m dot steam, H3 less H4. H1 corresponds to a temperature of 290 Kelvin, and H2 corresponds to a temperature of 320 Kelvin for the air. H3 corresponds to our saturated vapor state, and H4 corresponds to our saturated liquid state of our condensing steam. Thus, the mass flow rate for the steam to air is H2 per H1 per H3 less H4. Using the values from our tables, we find that our mass flow rate of our steam to that of air has to be 0.0134. Now, if we evaluate our entropy rate balance equation, we'd have m dot air times the quantity S1 less S2 plus m dot steam times the quantity S3 less S4 plus sigma dot is equal to 0. That is, on a per flow rate basis of our air, sigma dot per m dot air is equal to S2 less S1 plus m dot steam per m dot air times the quantity S4 less S3. Now, applying the values from our table, recalling that we already solved for S2 less S1 via our standard entropy, and using S4 and S3 from our steam tables, our sigma dot per m dot of our air would be equal to 0.09892 kilojoule per kgK plus our mass flow rate ratio, 0.0134, times the difference of our entropy values, minus 6.0568 kilojoule per kgK. Or our sigma dot per m.air is equal to 0.178 kilojoule per kg/K. We see that the rate of entropy production per our mass flow rate of our air for system 1 is 5.56 times greater than system 2. Thus, thermodynamically speaking, system 2 is better for heating the air.